Welcome to Grandpa's Late Nights. It's so good to have you here. Pull the blanket up a little higher, would you? There. Settle in. Wherever you are tonight, whatever corner of the world you've carried yourself off to, I'm glad you found your way to the porch. There's a chair here that's been waiting for you, and the light's on, and there's nowhere either of us has to be. And before we get going, just a small thing, the kind of thing an old man asks for. If you like these slow, sleepy little wanderings of ours, a quiet like or a tap on that subscribe button, it really does help this little channel keep going. Small creators like me lean on that more than you'd think. And to those of you who've already done it, who keep coming back night after night, well, thank you. Truly. You make an old man feel less alone in the dark. So tell me, where in the world are you watching from tonight? What time is it in your corner of the night? Is it raining where you are? Or still? Or cold? I always like to imagine all of you out there, scattered across the whole turning earth, lying in your beds with your eyes already half shut, all of us looking up at the same sky from 1,000 different windows. There's something in that. We'll come back to it later, I think. Now I should warn you the way I always do. I'll try my best not to make tonight's story so interesting that it keeps you awake. But if it does, well, at least you'll have learned something on your way to morning. That's a fair trade, I think. And if you drift off before I'm done, before we reach the end of it, that's perfectly all right. The stars will still be there. The story will still be here. None of it's going anywhere. You don't have to hold on to a single word. You don't have to understand all of it, or even most of it. Just let my voice be a sound in the room while you sink down into sleep. That's all this is. That's all it ever needs to be. We'll go slow tonight. Slower than usual, maybe. Because the thing I want to tell you about is one of those great, big, quiet puzzles, the kind that sits at the very edge of what people know. And the only honest way to walk towards something like that is slowly. One small step at a time. No rush. No rush at all. So, let me tell you about a strange little argument the universe is having with itself. Here it is, the whole shape of it, before we wander into the middle. There are two ways that very careful people have learned to measure how fast the universe is growing. Two completely different ways, two roads to the same place. And here's the funny thing, the thing that won't leave the scientists alone at night. The two roads don't meet. They give two different answers. And the answers won't come together no matter how hard anyone tries. Now you might think, well, that's just because the measuring is hard, and it is hard. But here's the part that turns the whole thing strange, the part I want you to carry with you into sleep tonight, because it's the heart of everything. Usually when people get better at measuring something, the answers come closer together. That's how it's supposed to work. You build a sharper ruler, a steadier hand, a finer eye, and your guesses tighten up and crowd in around the truth like moths around the porch light. The closer you look, the more everyone agrees, but not here. Not with this. With this one, the better they measure, the further apart the two answers drift. As the rulers get sharper, the gap doesn't close. It widens. The two numbers don't reach toward each other. They pull away. And that little backwards fact is the thread we're going to follow tonight all the way down into the dark. Because it shouldn't happen. It really shouldn't. And nobody is quite sure why it does. Let me say it plainly. The way I'd say it sitting right beside you. Imagine you've got two clocks, two good clocks, both made by careful people, both wound tight and cared for, and you set them both going at noon, and you go away, and you come back, and one clock says it's 3 in the afternoon, and the other says it's 20 past 3, and you think, well, one of them's a little off, I'll just nudge it. But then you take both clocks apart and clean every tiny gear, and oil every spring, and put them back together better than before. And you set them going again. And this time, the gap between them is bigger, not smaller. Bigger.
The more you fix them, the more they disagree. That's the puzzle. That's the whole thing in a nutshell you could hold in your hand. Two clocks, both excellent, both cared for, that refuse to agree and disagree more the better you make them. Only the clocks aren't clocks. The clocks are the whole universe, and the time they're keeping is the speed at which everything everywhere is flying apart.
So let's slow down and unfold that gently like an old map on the kitchen table. You've probably heard somewhere along the way that the universe is expanding. That's a true thing and a strange one, and we don't think about it nearly enough. It means that space itself, the empty room between the galaxies, is quietly stretching, getting bigger. Not the galaxies flying out through space like shrapnel from an explosion. No, not quite that. It's the space between them that's growing. Imagine a loaf of raisin bread rising in a warm oven. The raisins themselves don't move, not really, but the dough between them swells. And so every raisin drifts away from every other raisin just because there's more and more bread in between. That's us. That's everything. We're raisins in a loaf that never stops rising. And because every bit of space is stretching, the farther away a galaxy is, the faster it seems to rush away from us. A galaxy nearby drifts off slowly. A galaxy twice as far drifts off twice as fast. 3 times as far, 3 times as fast. Because there's 3 times as much stretching space in between. It's a steady, simple rule, really. The farther, the faster. And the number that captures how fast all this stretching happens, the number that sets the pace of the whole rising loaf, that number has a name. The scientists call it the Hubble constant. They write it down as H with a little 0 tucked beside it. H0, they say. Don't let the name trouble you. It's just a name for a speed. It's the answer to a simple question. How fast is the universe growing right now?
And the way they write that speed down looks like a mouthful. So let me untangle it for you. Slow and easy, one knot at a time. They measure it in something called kilometers per second per megaparsec. I know it sounds like a spell, but it's gentler than it looks.
Start with the megaparsec. A megaparsec is just a distance, a big one, about 3.25 million light years. And a light year, remember, is how far light travels in a whole year. And light is the fastest thing there is. So a light year is already a distance that staggers the mind, and a megaparsec is over 3 million of those. So a megaparsec is a great gulf of space, the kind of distance you'd lay between one galaxy and a far-off neighbor. Hold that. A megaparsec is a chunk of the heavens, 3.25 million light years wide. Now, kilometers per second per megaparsec, all that mouthful is really saying is this. For every megaparsec of distance you go out, things are flying away that much faster. So if the number is, around 70, then a galaxy 1 megaparsec away is rushing off at about 70 kilometers every second. And a galaxy 2 megaparsecs away twice as far is rushing off at about 140 kilometers every second. Twice the distance, twice the speed, just like the raisins. The number tells you how much speed you add for every step out into the dark. So that's the Hubble constant, that's H0, a single number that sets the pace of the entire expanding cosmos. One number to describe how fast all of creation is unfurling. You'd think there'd be just one right answer to a question like that. One true number sitting out there, waiting to be found. And here's where the trouble begins, because there isn't one answer, there are two. Two stubborn, well-defended, carefully measured numbers, and they don't match. One way of measuring gives a number of about 67.5. 67.4 to be precise, and the precision matters here. It matters more than you'd guess. The other way gives a number of about 73, and 73 is not 67.5. They are simply not the same number. The gap between them is around 5 or 6, which doesn't sound like much when I say it out loud like that, sitting here on the porch. But in this work, that gap is an enormous thing. It's a difference of around 8 or 9%. Nearly a tenth of the whole answer, just gone, just unaccounted for, depending on which road you walk to get there.
And both roads are good roads. That's what makes it ache. If one of the methods was sloppy, if one team were cutting corners or fooling themselves, you could just throw that one out and keep the other. But that's not what's happening. Both methods are built by some of the most careful people who have ever lived, checked and rechecked, and both of them stand by their answer. One says 67.5, one says 73, and neither will budge.
So let me give the two roads their proper names gently, so you'll recognize them later when we walk down each one. Because we will walk down each one tonight, slowly, hand in hand, all the way to the end. The first road, the one that gives the lower number, around 67.5, we'll call the early road, because it reaches all the way back to the very beginning of things, to the infant universe, to the oldest light there is. We'll get to how it works, I promise, but for now just hold the picture. The early road. It listens to the baby universe, just after it was born, and from that faint old whisper, it works out how fast things ought to be growing today. About 67.5. The second road, the one that gives the higher number, around 73, we'll call the late road, because it works here and now in the universe of today. It measures real galaxies out the window, near ones and far ones, and clocks how fast they're drifting away from us right now tonight. And when it adds it all up, it gets about 73. The early universe says 67.5. The late universe says 73. The beginning of time and the present moment cannot agree on how fast the cosmos is growing. And that's the whole quiet scandal of it. Now, I told you a moment ago about the question I want you to fall asleep on. The title of our little story tonight is that the universe is expanding faster than it should. And the very first thing a thoughtful person ought to ask, the question I'd ask if you told me that is, well, hold on. Faster than it should? Faster than what? Should? According to whom? Who decided what speed the universe is supposed to grow at so that we could turn around and catch it going too fast? It's exactly the right question, and the answer is one of the most beautiful and slippery ideas in all of this. So, let me lay it down softly, and we'll pick it back up later when we're ready for it. That word, should, is doing an enormous amount of work. The should comes from the early road, from the baby universe, because the early road doesn't really hand you a measurement of today at all, not directly. What it does is something subtler and stranger. It looks at the infant universe, at what it was made of and how it was shaped in those first young moments, and then it takes our very best recipe for how a universe like that grows up, and it runs that recipe forward through nearly 14 billion years of history, and out the other end comes a prediction. This, says the recipe, this is how fast such a universe should be expanding by now, about 67.5. So the should is a prediction. It's what the universe ought to be doing today if we've understood the recipe correctly, if we know all the ingredients. And the late road, the 73, that's what the universe is actually doing today, measured straight out the window here and now. And those two things, what it should be doing and what it is doing, don't match. Sit with that for a moment, because it changes the whole feeling of the thing. The argument might not be between two telescopes at all. It might not be that someone measured wrong. It might be that the recipe is missing an ingredient, that somewhere in those 14 billion years, the universe did something we didn't write down, something we don't yet understand. The gap between 67.5 and 73 might be the size and shape of a thing we don't know about the cosmos. A missing word in the oldest recipe there is. But I'm getting ahead of myself, and we've all the night for this. Let me go back to that backwards little fact, because it's the spine of everything, the bone the whole creature hangs from, and I want it settled deep in you before you drift off. The gap is growing. When people first started noticing that the two roads gave different answers, years ago now, it wasn't alarming at all, because back then the measurements were rough, And when a measurement is rough, it comes with a kind of fuzziness around it, a little cushion of uncertainty. The scientists draw it as error bars, little whiskers reaching out on either side of the number, saying the truth is somewhere in here, give or take. And back in those early days, the whiskers on the two numbers were long and generous. The early road's fuzziness and the late road's fuzziness overlapped. They touched, and as long as they touched, there was no real quarrel. The two numbers could both be shadows of a single true number hiding in the place where their fuzzy edges met. No trouble. Just two rough guesses at the same thing. But the scientists, being who they are, kept working. They built better instruments. They gathered more light. They checked their checks and corrected their corrections. And slowly, year by year, the fuzziness shrank. The whiskers pulled in. The numbers grew sharp. And here is the thing that should not have happened. As the whiskers pulled in, the two numbers did not slide together. They held their ground. 67.5 stayed 67.5, only now with hardly any fuzz around it at all, a number you could trust. And 73 stayed 73, sharp and sure and proud. And the little cushions of uncertainty that used to overlap, that used to touch and let everyone sleep easy, those cushions shrank back from each other until they no longer touched at all. A clean gap opened up between them. Empty space, no overlap. Two sharp numbers staring at each other across a divide that the sharpening was supposed to close and instead only opened wider.
That's not how this is meant to go. You understand that, don't you? Even half asleep. When two people are guessing at a thing in the dark, and you hand them both a flashlight, they're supposed to agree more, not less. The light is supposed to bring them together, but here, the brighter the light got, the more certain each one became that the other was wrong. The precision didn't dissolve the conflict, it sharpened it into something undeniable.
There's a way the scientists measure how serious a disagreement like this has become, and it has a name worth knowing because it tells you just how far past a coincidence this thing has traveled. They count it in something called sigma. You don't need the arithmetic of it. Just the feeling. 1 or 2 sigma is a shrug, could easily be chance, could be nothing, the kind of difference that vanishes with the next good measurement. But the further up you go, the harder it gets to call it luck. And there's a line, a famous line in this work, drawn at 5 sigma. 5 sigma is the line where scientists allow themselves to stop saying maybe and start saying, we have discovered something. It's the very same bar, the exact same threshold of certainty that they demanded before they would announce that they'd found the Higgs boson, that famous particle, years back. 5 sigma means the odds of the whole thing being a fluke, a trick of chance, are something like 1 in 3.5 million. You don't cross 5 sigma by accident. And this disagreement, this stubborn quarrel between 67.5 and 73 has crossed it. It sits up around 5 sigma now, which means by every rule these careful people have set for themselves, it is no longer a maybe, it is real. The two roads really do disagree, and the disagreement is as solid and certain as the discovery of a new particle. Only here's the strange and lovely difference. When they crossed 5 sigma for the Higgs, they were crossing it to announce a triumph, a new thing found, a box ticked, a prize won. But here they've crossed that same proud line, summoned that same towering certainty, and what they're certain of is a contradiction. They are 5 sigma sure that two things that cannot both be true are both somehow standing right in front of them, refusing to back down. They've used the tool of discovery to confirm, with the highest confidence they know how to muster, that something doesn't add up. That's a peculiar place for science to find itself, certain of a problem, confident in a wound. And it has a name, this whole quiet crisis. They call it the Hubble tension. Tension like a rope pulled taut from both ends, humming, holding, refusing to snap, refusing to slacken. The Hubble tension. And it may be, some of the cleverest people alive will tell you, it may be the most important unsolved problem in all of cosmology right now. The loose thread that, if you pulled it, might unravel and reweave our whole picture of where everything came from and where it's all going.
And isn't that something to fall asleep beside? That right now, tonight, while you and I sit here on this quiet porch with the light on, there are people in observatories all over the world, in the cold blue glow of their screens, staring at these two numbers and turning them over and over, trying to understand why the universe won't tell them a straight story about how fast it's growing. They don't know. Not yet.
The smartest people we have, with the finest machines we've ever built, looking at the oldest light there is, and they simply do not know why the early universe and the late universe disagree. And that not knowing isn't a failure, you understand. It's the most exciting thing in the whole field. It's the edge of the map. It's the place where the next great discovery is hiding, waiting in the gap between two numbers. So that's our story for tonight. That's the shape of the whole thing laid out gentle on the table. Two roads, two numbers, 67.5 from the beginning of time, 73 from the present moment. A gap of 8 or 9% that should have closed and instead has only opened wider, sharpened by every new and finer measurement, until it crossed the great line of certainty and became a real, undeniable contradiction sitting at the heart of how we understand the cosmos. The universe is expanding faster than it should, faster than the oldest recipe predicts, and nobody yet knows why. Now, the rest of the night we're going to walk down each of those two roads slowly, the way you'd take a path you love, stopping to look at everything. We'll walk the early road first, back to the afterglow of the very beginning, to the oldest light in existence, to a great telescope that listened to the baby universe and worked out, from its faint old whisper, just how fast everything ought to be growing today. And then we'll walk the late road, the one that climbs up through the present-day sky, one careful step at a time, like a ladder leaned against the heavens, each rung resting on the one below it. We'll meet the people who built these roads. We'll find out why each one is so trusted and so hard to argue with. And we'll come, at the very end, to the menu of strange and wonderful guesses about what the missing ingredient might be. The things that could mend the gap if only one of them turned out to be true. But none of that needs to trouble you now. We've got all the time in the world, you and I. There's no hurry on this porch. There never is. So let's take the first slow step together onto the early road, back toward the beginning of everything. And the first thing we'll need to understand before we can understand anything else is a kind of light, a very old, very faint, very patient light that has been traveling toward us for nearly the whole age of the universe and is falling, even now, even tonight, ever so softly, all around you in the dark. But before we get to that light, I should tell you the name of the thing we're chasing tonight, because the whole mystery hangs on a single number, and that number has a name. We call it the Hubble constant. And if you write it down, it looks like a letter H with a tiny little zero tucked beneath it. H0, some folks say. H0, say others. It's the number that tells us how fast the universe is stretching itself open. Now, here's the curious thing about that number. It doesn't come out in plain old miles per hour, the way a car on the highway might. It comes out in something stranger. Kilometers per second per megaparsec. And I know, that's a mouthful, and it sounds like something you'd need a chalkboard for, but you don't. Stay with me a moment, here in the quiet, and I'll show you it's gentler than it sounds. A megaparsec is just a distance, a very large one, granted. It's about 3.25 million light years, so far that the light leaving the far side of it would have set out before the first human ever looked up and wondered. Hold that in your mind. 1 megaparsec, a great gulf of empty space with galaxies scattered across it like lamps in distant windows. Now, the Hubble constant says this. For every megaparsec of distance between us and some far-off galaxy, that galaxy is drifting away from us at a certain speed. If the number is 70, then a galaxy 1 megaparsec away is sliding off into the dark at about 70 kilometers every second. And a galaxy twice as far, 2 megaparsecs out, is moving twice as fast, 140 kilometers a second. The farther away a thing sits, the faster it flees. Not because anything is pushing it, mind you, but because the space in between is swelling like dough rising in a warm kitchen, carrying everything along with it. That's all the number is. A measure of the rising, a measure of how quickly the loaf of the cosmos is growing.
And you'd think, wouldn't you, that a number like that would be a settled thing by now? We've got the finest telescopes ever built. We've got satellites flung out past the moon, parked in the cold and the quiet where they can stare at the sky without a single cloud in the way. You'd think with all of that, the scientists would have written the number down long ago, underlined it twice, and gone home for the night.
But they haven't, and that's the strange and beautiful trouble at the heart of all this, because there are 2 great ways to measure that number, 2 roads as I called them, and the 2 roads do not agree. Picture it like this. Picture 2 old clocks on a mantelpiece, good clocks both of them, handsome, well-made, wound by careful hands, and every night you check them, and every night they tell you a slightly different time, not wildly different, just enough that you'd notice, just enough to keep you standing there, frowning, wondering which one to trust. That's where the cosmologists are now. 2 clocks, 2 answers. The first clock, the early one, the one that reads the oldest light, it gives a number of about 67.4 kilometers per second per megaparsec. And it gives that number very confidently, very precisely, with only the tiniest wobble of uncertainty on either side. The second clock, the late one, the one that climbs the ladder rung by rung up through the nearby sky, it gives a number of about 73, and it too gives its answer confidently. It too is sure of itself. Now 67 and 73, say them out loud here in the dark. They don't sound so very far apart, do they? A handful of numbers between them. The difference is only about 5 or 6 of those kilometer per second per megaparsec units. Around 9% all told, if it were the price of 2 loaves of bread at 2 shops down the road, you'd hardly cross the street to save it. But this isn't bread, this is the speed of the whole universe, and in a question that large, 9% is a canyon. 9% is a chasm you could lose entire theories in. And here is the part I want you to carry with you into your sleep tonight, even if you forget every other thing your old grandpa says. Here is the bone of the whole matter. When 2 careful measurements disagree, there's usually a comforting story about how it gets better. You measure again, more carefully. You build a sharper instrument. You gather more light, more nights, more patience, and slowly, the 2 answers drift toward each other and shake hands in the middle. That's how it's supposed to go. That's the whole faith of the thing, that the truth is one number and better looking brings you nearer to it. But that is not what happened here. Here, the opposite happened. As the years went by and the telescopes grew finer, and the satellites grew colder and quieter and more exact, as the people on both roads worked harder and measured better and pinned down their answers tighter than ever before, the 2 numbers did not come together. They pulled apart. In the early days, when both clocks were still a little blurry, the wobble on each one was wide enough that they overlapped. Their uncertainties brushed up against each other, and you could tell yourself comfortably that the real answer lay somewhere in the fuzzy place where they met. no trouble, no mystery. Just a thing not yet measured well enough. But then the measuring got better, and the wobble on each number got smaller. The early clock grew more sure it was 67.4. The late clock grew more sure it was 73. And as each one tightened, as each one narrowed down toward its own answer, the gap between them did not close. It opened. The two ranges peeled away from one another like two hands that had been almost touching and then drew slowly back until there was clear air between them. A space no measurement could bridge, a space that should not be there. That is the thing I keep turning over late at night on a porch like this one. Sharper eyes were supposed to settle the argument. Instead, sharper eyes made the argument worse. The better we looked, the surer we became, not of the answer, but of the disagreement. And there's a question hiding under all of this, a small one, that we ought to say out loud before we go any further. People say the universe is expanding faster than it should, but you've a right to stop them there and ask, faster than what? Faster than what exactly? What's the should? Where does it even come from? Because a thing can only be too fast if you know how fast it ought to be in the first place. The car is speeding only if you know the limit on the sign, and so somewhere there has to be a sign, somewhere there has to be a number that says here is how fast this universe ought to be growing, given everything we know about what it's made of and how it began. That's the early road, that's the 67.4. That number isn't really a reading of today at all. And we'll get to that, we'll get to just how strange that is, because it's one of the loveliest twists in the whole tale. But for now, just hold the shape of it. One number is a kind of expectation, a prediction handed down from the beginning. And the other number is what we actually find when we go out into the night and measure the sky as it is right now. The should is the prediction, the is the measurement. And the trouble, the whole trouble, is that they don't match. So that's the canyon we'll be walking the rim of all night long. 67 on one side, 73 on the other, a gap that grows wider the harder anyone looks, and somewhere down in the dark of it maybe a missing piece of the universe that nobody's found yet. But we won't reach it tonight by rushing, we never do, so let's go back now, the way I promised, all the way back to that first faint, patient light I told you about, the oldest light there is. And what a light it is. Settle in for a moment if you would. Let yourself feel the weight of the blanket, the softness of wherever you've landed tonight, because we're going somewhere extraordinary, and the going is slow, and the slow is exactly the point. We're going back to the beginning. Not the beginning of a country, or a civilization, or even a solar system. We're going back to the beginning of everything, or as close to it as any light has ever carried us. 13.8 billion years ago, give or take, there was an event we call the Big Bang. And I want to be careful here, careful in the way you'd be careful handling something very old and very fragile. We don't fully understand it. Nobody does. We have excellent models, beautiful mathematics, observations that fit the shape of it remarkably well, but the event itself, the very first instant, remains genuinely outside the reach of our current physics. So when I say the beginning, I mean the beginning of the universe as we know how to describe it, which is still, I think, breathtaking enough. For a very long time after that beginning, the universe was not transparent. It wasn't dark the way a room is dark when you switch the light off. It was something stranger. It was opaque the way the inside of the sun is opaque. There was light everywhere, but it couldn't go anywhere. It couldn't travel. It was trapped. Imagine a fog so dense that even a photon, a particle of light, the fastest thing there is, couldn't move more than a very short distance before colliding with something else. The early universe was like that. It was a hot, dense, luminous soup of matter, and radiation all tangled together, all crashing into each other, all too close and too energetic for anything to disentangle. Protons and electrons wanted to join up into neutral hydrogen atoms the way they do now everywhere in the cool, quiet universe, but the radiation was so fierce that it kept stripping them apart before they could. Every atom that tried to form was immediately broken back into its pieces, and so the light stayed trapped. And so the universe stayed opaque. For roughly 380,000 years, this went on. And then slowly, though slowly in the cosmic sense, which can still be a very abrupt thing by human standards, the universe cooled enough. The expansion had stretched it, diluted it, drained away the fierce energy that kept tearing atoms apart. And around 380,000 years after the beginning, protons and electrons finally got to do what they'd been trying to do all along. They combined. Neutral hydrogen atoms formed and stayed formed, and the moment they did, the fog lifted. Light, all that light that had been trapped in the soup, suddenly had nowhere to collide. The universe went from opaque to transparent in cosmological eye blink, and all that light streamed free in every direction into what had just become a clear and cooling cosmos. That's the light we're talking about. That's what cosmologists call the cosmic microwave background, the CMB. It isn't a metaphor, it's a real, physical thing, photons that have been traveling through the universe for 13.8 billion years, coming from every direction in the sky, arriving at our telescopes even right now. As you lie there, photons from the CMB are passing through you, through the walls of wherever you are, through the earth beneath you. Ancient, patient, unstoppable light, the oldest electromagnetic signal in the universe, carrying information about what the cosmos looked like when it was a mere infant. And the word background is good actually, it's a helpful word. Because these photons come from every direction equally, but more or less, they form a kind of wallpaper behind everything else, a uniform glow that fills the whole sky if you know how to look. Ordinary telescopes tuned to visible light can't see it, but microwave detectors can. And when you look at the cosmic microwave background with the right instruments, you see a sky that glows at a temperature of about 2.7 degrees above absolute zero. That's almost as cold as it gets. It was much hotter when it was first released, back when the universe was 380,000 years old, closer to 3,000 degrees then. But the expansion of the universe has stretched those photons, pulled their wavelengths longer and longer over billions of years, cooling them down to almost nothing. They've been on a very long journey, and the journey has cost them. Now, at this point, you might be drifting, and that's perfectly fine. The idea I want you to carry with you, loosely, softly, is just this. We can see this ancient light. We can map it. And it has things written in it, very faint, almost invisible things that tell us about the universe as it was a long time ago. The Planck satellite is the instrument that read those things most precisely. Planck was an ESA mission, the European Space Agency, and it launched in 2009 and spent years orbiting the Sun at a special gravitational point about 1.5 million kilometers from Earth, far enough from our own world's warmth to keep its detectors at the extraordinarily low temperatures they needed to work. It was observing the CMB the entire time, building up a map of the whole sky in microwave light. And in 2018, the Planck team released their final, refined results. Those results are the ones that matter most to our story tonight. What Planck was mapping in exquisite detail were tiny temperature variations in the cosmic microwave background. And when I say tiny, I mean astonishingly tiny, ripples of about 1 part in 100,000. If the average temperature of the CMB is 2.7 degrees, these ripples are fluctuations of about 1/27th of a thousandth of a degree. You can barely write the number, let alone intuit how small it is. A thermometer in your kitchen can't measure variations 1,000,000 times larger than these, but Planck could. Planck mapped these variations across the entire sky, building up what cosmologists call the CMB power spectrum, a kind of fingerprint, a precise statistical portrait of which sizes of temperature ripple appear how often across the sky. And in that fingerprint is encoded remarkably almost everything about the early universe. The density of matter, the geometry of space, the expansion rate, the composition, because those tiny ripples aren't random. They have structure, they come from something very specific that was happening in that hot, dense plasma before the fog lifted. Here's what was happening. Before recombination, before those atoms formed and the fog cleared, the plasma was ringing. Sound waves were moving through it. Not sound the way you hear it, vibrations in air, but pressure waves, acoustic oscillations, compressions and rarefactions that moved through the tightly coupled matter and radiation soup. Regions that were slightly denser would collapse under their own gravity, compressing, heating up, and then the pressure of all that trapped radiation would push back, expanding them again, and then gravity would pull them inward again, and so on. A cycle, a ringing, the universe as a cosmic bell struck at the Big Bang and vibrating. Now those sound waves could travel, but they could only travel at a specific speed, the speed of sound in the plasma, which was a significant fraction of the speed of light, something like 50 or 60%, and they had a limited amount of time to travel from the Big Bang to the moment of recombination when the ringing stopped. 380,000 years. So when recombination happened, when the fog lifted and the light streamed free, those sound waves froze. They stopped exactly where they were. The cycle of compression and expansion ended at a specific phase, and the maximum distance those sound waves could have traveled in that time, the distance between the point of origin and the leading edge of the outermost wave, became frozen into the CMB as a preferred scale, a physical ruler written into the fabric of the ancient light. Cosmologists call this the sound horizon, and it's roughly 150 megaparsecs, about 480 million light-years, in co-moving distance, meaning corrected for the expansion that's happened since. That's the ruler, that's the yardstick. A feature in the CMB and also in the way galaxies are distributed today that corresponds to this frozen wave. And here is where it gets beautiful in a quiet, surprising way. If you know the physical size of a ruler, if you know it's actually 480 million light-years long, and you can measure how big it appears to look in the sky, then you can calculate how far away it is. And from how far away it is, and in which direction, and how things are moving, you can work backwards and forwards through the history of the universe and figure out, among other things, how fast it's expanding. That's what Planck did. It measured the angular size of this frozen acoustic feature, the sound horizon, in the CMB sky. It measured how large those ripples appear from where we're sitting, and it combined that with the rest of the CMB's statistical fingerprint, the way different sizes of ripples stack up against each other in the power spectrum, and fed all of that into the standard model of cosmology. The standard model of cosmology has a name, LCDM, pronounced lambda CDM. The lambda refers to the cosmological constant, the symbol Einstein used, the same one he thought was his biggest mistake and then turned out to be correct after all, which represents dark energy. The CDM stands for cold, dark matter. So LCDM is a model of a universe made of roughly 5% ordinary matter, the kind we're made of, atoms, molecules, the periodic table, everything we can touch and see, about 27% cold, dark matter, which doesn't emit or absorb light but has gravitational weight and shapes the universe, and about 68% dark energy, which is the mysterious pressure responsible for the acceleration of the expansion. That's the recipe. LCDM says those are the proportions of the universe's ingredients, and given those proportions and the rules of physics as we know them, you can predict how a universe starting the way ours did should evolve over time. And Planck, having measured the CMB precisely, took all of that data and ran LCDM forward. Not like running a simulation in an afternoon. This is the theoretical machinery of the whole field, refined over decades. But the principle is almost like baking. You know the starting ingredients, you know the recipe, you let time do what it does, and at the end you predict what you should get. And what Planck predicted for the expansion rate of the universe today was 67.4 kilometers per second per megaparsec, plus or minus half a kilometer per second per megaparsec. That's the error bar, 67.4, with a precision of about half a unit in either direction. That number is the early roots answer to the Hubble constant. That's what the beginning of the universe, mapped with extraordinary care, predicts that today's expansion rate should be. And you see now what I meant when I said we'd get to just how strange the 67.4 is, because that number is not a reading of today. Nobody put a ruler alongside a galaxy a megaparsec away and measured its speed and got 67. The Planck measurement is of the infant universe, the universe at 380,000 years old. What we got is a measurement of then. What the number is a prediction of now. Run forward through 13.8 billion years of LCDM. A prediction, not an observation of the present. An extrapolation through the entire history of the cosmos using the standard model as the bridge, which means, and this is the thing to hold gently because it matters enormously, if the standard model is right, those two numbers should agree. If LCDM correctly describes the universe from beginning to now, then the prediction and the local measurement should land on the same value. Within their error bars, they should shake hands, but they don't. The local measurement, the one we'll get to in a little while, comes back around 73, not 67.4, 73, and the gap between those two numbers, carried through the precision of both measurements, now sits at a statistical significance of around 5 sigma. Sigma is a measure of how likely a disagreement is to be a fluke. 1 sigma, it might just be noise. 2 sigma, interesting but not alarming. 3 sigma, cosmologists start paying attention at conferences. 4 sigma, they stop sleeping easily. 5 sigma is the threshold physicists use to declare a genuine discovery. It's the bar that was crossed when the Higgs boson was confirmed at CERN in 2012. At 5 sigma, the chance of the discrepancy being a random accident is roughly 1 in 3.5 million. So we've reached the Higgs discovery level of confidence. Only instead of confirming something exists, we're confirming that 2 very careful, very rigorous measurements of the same thing disagree. That's not a comfortable place for a field to be. It's an exciting one, but it isn't comfortable. And the most unsettling part of it, with the detail that sits and nags at you the longer you think about it, is that this is not a disagreement that came about because someone was careless. It's not a case where one team made a mistake and the other team caught it. Both measurements have been checked and double-checked and checked again by independent groups using different instruments and different techniques. Both have tightened their error bars over the years. And as the error bars got tighter, as both measurements got more precise, the gap didn't close, it stayed open. And then, quietly, implacably, it got wider. That's the thing that should strike you. That's the thing that strikes every cosmologist who spends time with it. Usually, when a discrepancy exists between 2 measurements and both teams work harder and get more precise, what happens is the numbers creep toward each other. The error bars overlap. Everyone breathes a sigh of relief, and the tension evaporates. That's what happened countless times before in physics. Measurements that seemed to disagree, until they didn't. But here, something different happened. The Planck results got sharper, the local distance measurements got sharper, the overlapping error bars pulled apart and stopped touching. The gap, rather than dissolving, became more clearly defined, more undeniable. Which means, maybe possibly tentatively I can cure that this isn't a measurement problem. Maybe there's something real here. Maybe the universe between then and now, between the infant cosmos Planck measured and the grown cosmos we observe, contains something the recipe doesn't account for. Some ingredient that LCDM doesn't include. Something that changed the expansion history in a way the standard model doesn't predict. Or, and this is the disciplined scientist's constant companion, maybe there's an error somewhere that nobody has found yet. A systematic mistake, a subtle bias, something that slipped through every check and cross-check and still hasn't been caught. The universe might be fine, our instruments might be slightly wrong. Both possibilities live honestly side by side, and knowing which one is true is what the whole field is working on right now. But before we get to that, and we'll get there, I promise, we have all night. Let's stay with the early route, just a little longer. Let me tell you more about what the CMB actually looks like when you map it, because it's one of the genuinely beautiful things modern science has produced. Imagine a map of the entire sky, stretched flat the way you stretch a map of the Earth flat, knowing it distorts the edges. Now color every point in that map according to the temperature of the CMB at that point in the sky. Not the actual temperature, but the tiny deviation from average. The average is 2.7 degrees, and we've agreed that's the same everywhere to an extraordinary degree. But there are ripples, as I said, 1 part in 100,000. Map those, and what you see is a swirling pattern, patches of very slightly warmer and very slightly cooler, like the surface of something old and grand, like rings in wood, or the texture of ancient stone. These patterns are the amplified descendants of quantum fluctuations. Random quantum wiggles from the first instance of the universe, stretched out by the extraordinary expansion of the early cosmos into structures that became, eventually, the seeds of every galaxy and cluster of galaxies you've ever seen or will see. The Milky Way, the Andromeda Galaxy, the Virgo cluster, the great walls and voids of the cosmic web, all of it traces back, in origin, to tiny random flickerings in the quantum foam of the very beginning, preserved in this ancient light. And the particular pattern, the specific way the ripples of different sizes are distributed in the CMB sky, is what LCDM predicts. When Planck's measurements came back, the pattern matched the prediction with spectacular precision. The peaks and troughs of the power spectrum lined up almost perfectly with what the standard model expected. 67.4, with those tight error bars, sits squarely in the middle of a model that fits the CMB beautifully, which is part of what makes the tension so vexing. LCDM isn't a bad model that's barely hanging on. It's a model that fits its data exquisitely. It passes test after test. The CMB, the large-scale structure of the universe, the formation of light elements in the first minutes after the Big Bang, all of it fits LCDM to a precision that ought to make any physicist proud. The model earns its place. And yet here, on this one number, this one comparison between past and present, it seems to be off. Not by much, but by enough that the whole edifice might have a crack in it. That's the peculiarity of the situation. The model works almost everywhere, and the place where it might not work is the very comparison between where it came from and where we are now. Let's linger a moment on the sound horizon because it's worth really feeling what that means. 380,000 years after the Big Bang, the universe is cooling. The hot plasma is beginning to settle. For 380,000 years, pressure waves have been rippling outward through that plasma, moving at a significant fraction of the speed of light, which is still almost incomprehensibly fast, but for 380,000 years. The leading edge of those waves has traveled a certain distance from the origin, and at the moment of recombination, when atoms form and the fog clears and the light streams free, everything freezes. The wave stops right where it is, like a snapshot, like a photograph taken at exactly the moment a stone hits water. the rings of the ripple captured in mid-motion. And that frozen ring that preferred distance, that scale, is the sound horizon. Roughly 150 megaparsecs in the units cosmologists use, or about 480 million light-years. And it's not just a feature in the CMB, it's a feature in the distribution of galaxies too, because the matter that was swept up in those oscillations was the same matter that later collapsed to form galaxies. And so if you look at the three-dimensional map of where galaxies are, and we now have maps of millions of them, you find a slight tendency for galaxy pairs to be separated by distances corresponding to that frozen wave. A cosmic echo preserved in where the stars chose to live. It's one of those things that when you first encounter it, seems impossible. A sound wave from 380,000 years after the Big Bang, still visible today in the arrangement of galaxies across the sky. A physical ruler, 480 million light-years long, built into the universe itself, that we can use to calibrate our measurements. Baryon acoustic oscillations, they're called. BO. The baryons are the ordinary particles, i.e. protons, neutrons, and the acoustic oscillations are the sound waves, and the whole phrase refers to this phenomenon. The way ordinary matter was jostled by those ancient waves and left a statistical imprint on the cosmos that we can still read billions of years later. And here is the crucial thing about the sound horizon for our story. Its size, that 150 megaparsecs, is determined by physics in the early universe, by how fast sound could travel in the plasma and how long it had to travel before recombination. And those things depend on the composition of the universe, on how much ordinary matter was present, on how much radiation, on the geometry of space, all of which are things LCDM has parameters for. So if you measure the sound horizon in the CMB through the angular scale of those acoustic peaks in the power spectrum, and you measure it in the galaxy distribution through BAO surveys, and they agree, and you run the model forward through cosmic history, you get a prediction for H0. And that prediction, under LCDM as calibrated by Planck, is 67.4. That's the chain of reasoning. That's the early route, laid bare. It rests on measuring the plasma waves in the infant universe through the CMB, knowing the physics of how fast those waves moved, using the frozen wave scale as a ruler, fitting the whole picture to LCDM and extrapolating forward to today. Every step in that chain is exquisitely well supported. There are no obvious weak links. Smart, careful people have checked every assumption, tested every part of the model, looked for places where the chain might snap, and they haven't found them. And yet, 73. We'll get there, but not quite yet. Right now, I want you to just sit with the two things we've established this far into the night. We have a number, 67.4, that comes from reading the universe's oldest light and running the standard model forward like a recipe. And we have a mystery still ahead of us about a very different kind of measurement that gives a different answer. A measurement that doesn't look backward to the beginning at all. A measurement that looks outward at the universe as it is right now in this present era, using an extraordinary chain of stepping stones across the cosmos. That chain has a name too, the cosmic distance ladder, and it's both more concrete and, in some ways, more precarious than the early route. A sequence of calibrations, each one resting on the one before, reaching farther and farther out until it gets to galaxies moving so fast and far away that their velocity in the Hubble flow can be compared against their measured distance, and a value extracted. But here's the thing to notice as you lie there, somewhere in the quiet dark of your evening. The two routes, the early CMB route and the late distance ladder route, are measuring, in principle, the same thing. They're both trying to pin down the same number, the same property of the universe's expansion, and they disagree. They disagree by about 5 or 6 kilometers per second per megaparsec. which sounds small, but in a universe where the numbers themselves range between 67 and 73, 5 or 6 is almost 9%, and at 5 sigma it's not small at all. One way to think about it, a rough way, just to feel the scale, is to imagine two very meticulous surveyors, both independently measuring the same road. One starts from the known position of one end, uses all the physics of how roads were built, and calculates what the length should be. The other drives the road with a calibrated odometer. The first surveyor says, "Given everything I know, this road should be 67 kilometers long." The second surveyor says, "I drove it and it's 73. Both have their instruments calibrated, both have colleagues who check their work. Both get the same answer every time they repeat the measurement." That's the situation, not an accident of carelessness, a genuine, reproducible disagreement between two methods that should agree. And what cosmologists have been wrestling with, what the whole field has been turning over like a stone, looking for what's underneath, is the question of where the discrepancy lives. Is there something wrong with the early measurement? Is LCDM, despite its successes, quietly wrong about some aspect of the early universe that biases its prediction? Or is there something wrong with the late measurement? Some systematic error in the distance ladder that makes it read high, that makes the universe look like it's expanding faster than it really is? And this is the hard possibility, the one that keeps theorists up at night. What if neither measurement is wrong? What if both are right, and the universe between 380,000 years old and today did something the model doesn't account for? What if there's an ingredient missing from LCDM, some physics that operated between the early universe and now that changed the expansion history in a way we haven't captured? If that's the case, if neither telescope is mistaken and the gap is real, then the 67.4 and the 73 are both correct. The universe, at the time the CMB was released, was on a trajectory that should have produced 67, and the universe today is actually expanding at 73. Something intervened, something between then and now pushed or pulled the expansion harder than the standard model expected, and what that something might be is one of the most open, most actively debated, most genuinely unresolved questions in all of modern science. It's not a trivial adjustment. LCDM is built on decades of observation, on multiple independent lines of evidence that all converge beautifully. Any change to it, any new ingredient, would have to slip in quietly enough not to disturb all those other agreements. It would have to be hidden in some sense, making its influence felt in the expansion history without leaving fingerprints everywhere else. That's a tight constraint. The physicists who work on possible resolutions to the Hubble tension spend most of their time discovering that their proposed new ingredient breaks something else. The model is like a very carefully balanced mobile. Touch one piece and everything shifts. But we're getting ahead of ourselves, as I sometimes do when the night gets interesting. And you're here to drift, not to solve anything. The solutions, the proposals, the candidates, the possible new physics are coming later in our journey. For now, the thing to feel, to carry into the softer dark of almost sleep, is the shape of what Planck gave us. A satellite, drifting alone in space, 1.5 million kilometers from home, recording the faintest possible signal, photons that have been traveling for nearly 14 billion years, mapping a sky that glows in frequencies human eyes can't see, in a pattern of temperature ripples almost too small to measure. Building from that whisper of ancient light, a picture of what the universe was made of in its infancy, and from that picture, through the long, careful machinery of LCDM, predicting what the universe should be doing today, 67.4, plus or minus half a unit. The universe's own birth record interpreted through our best current understanding, telling us how fast things ought to be receding from each other. And somewhere out there, beyond the comfortable reach of familiar stars, Galaxies are receding at a pace that doesn't match the birth record. Not by much, but by enough. By a persistently, stubbornly, maddening enough. The fog lifted at 380,000 years. The light streamed free. And it has been traveling toward us ever since, carrying its message. We read the message carefully. We trusted it. We ran the numbers. And then we went outside and looked at the sky ourselves. Those are the two halves of the tension. The message from the past and the observation of the present. And now you know what the early route is, what it rests on, and what it actually tells us. Not a direct reading of today, but a prediction. A rigorously derived, beautifully supported, model-dependent prediction of what today should look like, given a universe that began the way ours did and evolved the way LCDM says it evolved. That prediction is 67.4. And now, gently, no rush, the night is still long and easy. We need to go the other way. Not backward to the beginning, but outward into the present sky. Rung by rung, stepping stone by stepping stone, all the way to the edge of the Hubble flow. We need to climb the distance ladder. But before we do, and you can let this be the last thought before you drift a little, or the first thought you carry into the next part of our journey, whichever comes first, I want you to hold one thing in particular, one detail that I find quietly extraordinary every time I return to it. The sound horizon, that frozen wave, 150 megaparsecs, 480 million light-years, written into the structure of the early universe and still visible today in the way galaxies cluster. A physical ruler built into the cosmos itself, set down at 380,000 years old and preserved all the way to now. There's no human hand in that ruler, no convention, no agreement about units, no decision about what a meter is. It's just physics. It's the distance sound could travel in a hot plasma in 380,000 years. That's it, a natural constant of the universe's own making, a scale handed to us as a gift by the Big Bang itself. And we're using it carefully, rigorously, with full awareness of every assumption involved. We're using a 480 million light-year ruler that the infant universe inscribed in light and matter to measure the grown universe's expansion. That's where 67.4 comes from. That's the sign on the road. And now we're going to see what the odometer says. So, the distance ladder, let me tell you what it is before we start climbing it, because the name is almost too modest for what it actually represents. A ladder suggests something you might find leaning against a garden wall, wooden rungs, a bit wobbly, something you'd hold on to with both hands. The cosmic distance ladder is nothing like that in size or complexity, and yet the metaphor holds in one essential way. Each rung depends on the one below it. You can't reach the third step without standing on the second. You can't stand on the second without the first being solid beneath you. The whole structure rises from the ground up, each level using the one below as its anchor, its calibration, its point of trust. And the ground, the very bottom rung, is something so simple and so old that it requires no physics beyond triangles. It's parallax. You've experienced parallax, actually. Right now, if you hold a finger up in front of your face and close one eye, then open that eye and close the other, your finger appears to jump sideways. It doesn't move. You didn't move. But the angle from which you're viewing it changed because your two eyes are a few centimeters apart, and that small separation is enough to make a nearby object appear to shift against a distant background. Astronomers do the same thing. Except the two eyes, in this case, are the positions of the Earth on opposite sides of its orbit around the Sun. 6 months apart, 299 million kilometers apart. From one side of the orbit, you photograph a nearby star. 6 months later, from the other side, you photograph it again. the star appears to have shifted very slightly against the distant background of much farther stars. That shift is your parallax angle. And from that angle, knowing the size of Earth's orbit, you can calculate the distance to the star with nothing but geometry. No assumptions about the star's brightness, no model of how stars behave, just triangles. For nearby stars, this is exquisitely reliable. The European Space Agency's Gaia satellite has measured parallax for over 1 billion stars in our galaxy with extraordinary precision. That's the ground beneath everything, the most fundamental rung, the one that doesn't need a rung below it. But parallax has limits. For stars even a few thousand light-years away, the parallax angle becomes vanishingly small. And for galaxies millions or tens of millions of light-years away, the distances we need if we're going to measure cosmic expansion, parallax is simply too tiny to detect. You need something else. This is where NGC 4258 comes in. NGC 4258 is a spiral galaxy about 23 million light-years from here. And inside its core, there are water masers. Masers are like lasers, but for microwave radiation rather than light. And these particular masers orbit the supermassive black hole at the center of NGC 4258 in a very precise disk. Because we can observe them with radio telescopes and track their motion over years, both how fast they move across the sky, which gives us their orbital speed, and how fast they're moving toward or away from us, which gives us their radial speed, we can calculate the physical size of their orbits, and from that, the geometric distance to the galaxy. No assumptions about stellar physics. No standard candle. Pure geometry extended outward, past parallax's reach, using the orbital mechanics of water molecules around a black hole. NGC 4258 is one of the anchor points of the late universe route. A step beyond parallax using a completely different mechanism, but still rooted in geometric model-independent measurement. It gives us a foothold at 23 million light-years, and that foothold is what allows us to calibrate the next rung, the Cepheids. Cepheid variable stars are perhaps the most important class of objects in the history of observational cosmology, and their importance was discovered not by a famous old professor with a long beard, but by a quiet woman working at a computing desk at the Harvard College Observatory in the early 20th century. Her name was Henrietta Swan Leavitt. Leavitt joined the observatory in the 1890s, initially as an unpaid volunteer, then later as a paid employee at 25 cents an hour. Her job, like that of many women known as computers at the time, was to study photographic plates. Glass plates, exposed to the night sky by telescope, showing stars as tiny dots of varying brightness. She measured, she catalogued, she worked methodically through thousands of images, and she was assigned to study the Magellanic Clouds, two small satellite galaxies visible from the southern hemisphere, a smudge and a slightly larger smudge hanging near the Milky Way in the night sky. She was looking specifically at a type of star called Cepheid variables. These stars pulsate. They swell and shrink in a regular repeating cycle, growing brighter and then dimmer, and then brighter again, like a slow, steady breath. Astronomers had known about Cepheids for decades, but nobody had worked out whether there was a pattern. Leavitt found one. In 1908, and then more completely in 1912, she published her discovery. Looking at Cepheids in the small Magellanic Cloud, she noticed something. The brighter ones took longer to complete their cycle. A Cepheid that pulsed over 30 days was intrinsically brighter than one that pulsed over 3 days. There was a clean, tight relationship between the period of the pulsation and the true luminosity of the star. This is now called the Leavitt Law, sometimes the period luminosity relation, and it is the second rung of the distance ladder. Here's why it's so powerful. Imagine you have a star and you can watch it pulsate. You can count the days of its cycle just by watching it grow bright and dim. From the period alone, from that cycle length, you can look up the Leavitt Law and determine the star's true brightness, its actual luminosity, in absolute terms. Now compare that to how bright it appears from Earth. A star that is genuinely very luminous but appears faint must be far away. The dimming follows the inverse square law. Double the distance, quarter the brightness. So if you know the true brightness and you see the apparent brightness, you can calculate the distance. Period tells you luminosity. Luminosity compared to apparent brightness tells you distance. It's elegant, almost unreasonably so. The critical thing, the thing that makes this rung reliable, is that it's anchored by the rung below. To use the Leavitt Law, you need to know not just the shape of the relationship, not just that brighter ones pulse slower, but the calibration, the absolute values. You need to know a Cepheid with a 30-day period is actually this bright in real physical units. And to know that, you need Cepheids whose distances you already know by other means, by parallax or by geometric methods like those used in NGC 4258, the Adam Riess collaboration, supernovae, H0 for the equation of state, led by Adam Riess, has spent years doing exactly this calibration with meticulous care. They use geometric anchors like NGC 4258 to nail down the absolute scale of the Cepheid distances. Then they use those calibrated Cepheids to reach across tens of millions of light years, and then they use them to calibrate the third rung, the type Ia supernovae. A type Ia supernova is a stellar explosion of almost unimaginable violence. The short version is this: a white dwarf, the dense, Earth-sized remnant of a dead star, in a binary system accumulates material from a companion. When it reaches a critical mass threshold, a runaway nuclear reaction ignites, and the white dwarf tears itself apart in a thermonuclear explosion bright enough to briefly outshine its entire host galaxy. Hundreds of billions of stars, and for a few weeks a single exploding stellar corpse outshines all of them. What makes these events so useful cosmologically is that they're remarkably consistent. The physics that triggers them, that critical mass threshold, means they explode with a similar peak luminosity each time. Not identical, but close enough that when you apply a well-understood correction for how fast they brighten and fade, you end up with what cosmologists call a standardizable candle, something whose true brightness you can infer from observable properties, not from knowing its distance in advance. And because they're so luminous, genuinely staggeringly luminous, you can see them across billions of light years, far, far beyond where individual Cepheid stars can be resolved. The Riess team uses Cepheids in nearby host galaxies to calibrate exactly how bright the type I supernovae in those galaxies actually are, in absolute physical terms. Then they use those calibrated supernovae to reach out into the deep Hubble flow, billions of light years away, where individual galaxies are just specks of light, but their supernovae can still be caught and measured. And out there, in that smooth region, far enough that local gravitational quirks wash out and the pure expansion of space dominates, they measure recession velocities and compare them to distances. They fit a line through the data. The slope of that line is the Hubble constant, and it comes out around 73 kilometers per second per megaparsec, 73.0 to be somewhat more precise, with an uncertainty of about plus or minus 1, so a range roughly between 72 and 74. That number, the local, ladder-measured number, is what's refusing to agree with 67.4. Now, here's the thing about a ladder. A chain is only as strong as its weakest link, and a ladder is only as trustworthy as its wobbliest rung. And the critics of the distance ladder have always known this. They've known it for decades. The Hubble constant has been notoriously difficult to measure precisely throughout its history, and the history of those difficulties is why, Even as the tension grew through the 2010s, many careful physicists said, wait, there might be a systematic error somewhere in the ladder, a subtle bias we haven't found yet, some source of contamination or misidentification that inflates the Cepheid distances, which inflates the supernova distances, which inflates the final H0. And the most obvious candidate for a long time was crowding. When you observe Cepheids in relatively nearby galaxies with the Hubble Space Telescope, you're looking at individual stars in a galaxy that might be tens of millions of light-years away. Even for Hubble, at those distances, stars start to blend together. A Cepheid might appear slightly brighter than it actually is because there are other stars very close to it on the sky, stars that you can't resolve as separate, stars whose light gets mixed into your measurement of the Cepheid. If your Cepheids look a bit too bright because they're contaminated by neighbors, you'd infer that they're a bit closer than they actually are. And that could propagate upward through the ladder, making everything seem nearer, which would raise your estimate of the expansion rate. It was a reasonable concern, not unreasonable at all. And then the James Webb Space Telescope launched. The James Webb Space Telescope is, in certain ways, an almost absurd piece of engineering. It's the largest space telescope ever built. It observes primarily in infrared light rather than visible light, which is crucial for astronomy because infrared penetrates dust clouds that would block or redden visible light. And it has a mirror nearly 6.5 meters across. You couldn't fit it inside the rocket that launched it, so the mirror unfolds like origami after deployment. It sits about 1.5 million kilometers from Earth at a gravitational balancing point called L2, where the combined gravity of the Earth and Sun keeps it stable enough to operate. The expectation, held by quite a few cosmologists who were hopeful that the Hubble tension would dissolve, was that when JWST turned its far sharper infrared eyes on the Cepheid host galaxies, it would find that yes, the Hubble Space Telescope had been fooled by crowding, that the Cepheids had been blended with neighbors, that the distances were systematically wrong, that 73 would come down, meet 67.4 somewhere in the middle, and the tension would evaporate. Beginning in 2023 and into 2024, the results started coming in. The JWST observations confirmed the Cepheid distances, not approximately, not within a revised larger error bar that could contain the discrepancy. The JWST measurements of the same galaxies, with its vastly superior angular resolution, with its ability to resolve stars that Hubble could not, with its infrared sensitivity, agreed with what the Henrietta Riess team had been finding. The crowding effect existed, but it was small, not nearly large enough to account for the gap between 73 and 67.4. The escape hatch was not a hatch at all, it was solid wall. This matters enormously for how we should think about the tension. Before JWST, a skeptic could say, we don't yet have the tools to rule out a systematic error in the Cepheid rung. Maybe it's there, and we just can't see it clearly enough. JWST was specifically designed to provide exactly that clarity. And when it provided the clarity, the answer was no, the error isn't there. Not at the scale needed. The Suez collaboration's analyses incorporating JWST data still pointed to an H0 in the low 70s. The local measurement is robust, the ladder holds, and that's where we arrive at the number that cosmologists now regard with a mixture of fascination and genuine unease: 5 sigma. In physics and statistics, sigma refers to a standard deviation, a measure of spread, how far something is from the expected average. If you flip a fair coin 100 times and get exactly 50 heads, you're at 0 sigma. If you get 60, you're a couple of sigmas away. If you get an extraordinary run of heads, so improbable that the chance of it happening by luck is less than 1 in a million, you're approaching 5 sigma. 5 sigma is the threshold physics adopted for what it calls a discovery, not a hint, not an interesting anomaly, not a result worth following up. A discovery. 5 sigma means the probability of the observed result occurring by random chance, if there were no real effect, is about 1 in 3.5 million. It's the same threshold that the experiments at the Large Hadron Collider used when they announced, in July 2012, that they had found the Higgs boson. 1 in 3.5 million odds of it being a fluke. That's what physicists decided means we found something real. The Hubble tension now sits at roughly 5 sigma. Some analyses put it at 4, some at close to 6. The exact number shifts depending on exactly which data sets you use and how you handle various technical choices, but it's in that range, and some analyses, carefully combining multiple independent measurements, push it right to that 5 sigma mark. Think about what that means: the standard threshold for declaring a particle discovered, a threshold set high precisely because physicists know how seductive false patterns can be, how easy it is to convince yourself you've found something that's just noise, or that threshold is being crossed. Except here, instead of crossing it to declare a discovery, we're crossing it to declare a contradiction. The universe is expanding faster than the standard model says it should be. Not probably, not maybe, not interesting if confirmed, 5 sigma confident. And yet it's not quite settled. Because 5 sigma assumes you've accounted for all the relevant sources of uncertainty. It assumes you haven't forgotten anything, and in a measurement problem this complex, spanning multiple independent techniques, and spanning the entire observable universe, the possibility that something has been forgotten cannot be entirely dismissed. This is why careful cosmologists don't say the standard model is broken. They say this is the most compelling evidence we've yet seen that something might be missing from the standard model. The distinction matters. It's the difference between honest science and overclaiming. But let's sit with 5 sigma for a moment, because it deserves to be appreciated. Wherever you are right now, whether you're in bed or on a couch or on a night train watching darkness go by outside the window, you exist in a universe whose expansion rate has been measured carefully and independently by 2 fundamentally different methods. One method reads light from the infant universe, just 380,000 years old, and uses the physics of the standard cosmological model to predict what the expansion should be today. The other method reaches out across the present sky, rung by rung up a chain built over decades by astronomers and physicists, and the quiet work of people like Henrietta Swan Leavitt, who measured photographic plates with 25 cents an hour and changed our understanding of the cosmos. And those 2 methods, one backward-looking, one present observing, disagree. They disagree by about 9%. They disagree with 5 sigma confidence. That gap isn't shrinking. And that is the strangest part of all. Normally, when a measurement is uncertain, when there's some discrepancy between 2 methods, you'd expect it to behave a certain way. As the measurements get better, you'd expect the error bars to shrink and the central values to drift toward each other. The outlier result gets refined and edges closer to the other. The more precise you become, the more both sides converge on the truth, because there's only one truth for them to converge on. That's not what's happened with the Hubble tension. As the Planck collaboration refined its CMB analysis, from early data releases to the final 2018 results, its central value stayed stubbornly near 67.4 and its error bar shrank. As Henrietta refined its distance ladder, more galaxies, better Cepheid samples, better supernova datasets, and now JWST confirmation, its central value stayed stubbornly near 73 and its error bar shrank. The 2 measurements have been getting more precise for over a decade, and as they got more precise, they got more incompatible, not less. The error bars, which once were wide enough to touch, now don't overlap at all, not even close. This is deeply unusual. If there were a systematic error somewhere, a bias in one method, a miscalibration in a rung of the ladder, an unaccounted effect in the CMB analysis, you would expect that as the measurements got better, as we looked more carefully and with better tools, the error would become apparent and the values would start to converge. Systematic errors usually become visible under scrutiny. They show up as inconsistencies between different subsamples. They create patterns in the residuals. They get exposed. The more scrutiny the Hubble tension has received, the more robust it has become. And this is why, after a decade of saying, let's wait for better data, many cosmologists have shifted to a different posture. Not panic, not proclamations that physics is broken, but genuine, serious interest in whether the tension might be pointing at something real. Something in the universe that the standard model, LCDM, the framework built on ordinary matter and dark energy as a cosmological constant, is missing. Something we haven't put into the recipe. There's a moment in this story that I keep coming back to. It's not a dramatic moment, not a single discovery or announcement. It's more of a quiet turning point in how a community of scientists began to think about a number. For years, throughout the 2010s, the tension sat at 2 sigma, then 3 sigma, then pushing 4. At 2 sigma, you take note. At 3, you start paying closer attention. At 4, you begin to write papers about it. But even at 4 sigma, you can still tell yourself, reasonably, that something will turn up. A systematic, a calibration error, a subtle effect nobody had thought to look for. The history of astronomy is full of confident measurements that turned out to be wrong, and reasonable people pointed to that history and said, let's be patient. Then the precision kept improving, the sigma kept climbing, JWST launched and provided the expected escape and didn't. The tension crossed 5 sigma not on a single dramatic date, but across a range of analyses from different teams using different methods. And the question quietly changed. It used to be, is the tension real or is it a measurement error? Now it's, if it's real, what does it mean? That question, what does it mean, is where we're headed next. Because the answer, or rather the collection of candidate answers, is where this story opens out into something genuinely strange and genuinely beautiful about the structure of the cosmos. But before we go there, I want to stay with Adam Riess for just a moment. Riess is the scientist at the head of the Cepheid collaboration. He shared the 2011 Nobel Prize in Physics, not for the Hubble tension, but for an earlier discovery. In 1998, his team and a competing team led by Saul Perlmutter and Brian Schmidt were both measuring type Ia supernovae at large distances, trying to determine how fast the universe's expansion was slowing down. The expectation at the time was that gravity would be putting the brakes on the Big Bang's expansion. The universe was expanding. That much had been known since Hubble's time, but gravity should be decelerating it. Both teams discovered that it wasn't decelerating. The expansion was accelerating. The universe is not just expanding, it is expanding faster and faster over time. And the only way to account for that acceleration was to invoke a form of energy permeating all of space, a repulsive pressure working against gravity that had been mathematically introduced by Einstein decades earlier, but then largely set aside. Dark energy, the lambda in LCDM. Riess and his colleagues built the scaffolding of modern cosmology. They established the tool, type Ia supernovae, as standardizable candles at cosmological distances, that then became the third rung of the distance ladder. And now, with that same tool, with that same careful approach of measuring and cross-checking and measuring again, the Riess collaboration under Riess is producing the number that refuses to match the prediction. He's not a fringe figure. He's not a contrarian with an axe to grind. He's one of the architects of the standard model using the tools he helped build to find a crack in the standard model's predictions. That's worth noting, not as an appeal to authority, but as a reminder that this tension isn't a challenge from outside the field. It's coming from inside the house, and across the room, if you'll allow the metaphor to stretch a little, is the Planck satellite's legacy. The Planck collaboration involved hundreds of scientists working for the European Space Agency over more than a decade. Their final data release in 2018 represents perhaps the most precise map ever made of the infant universe. Those temperature fluctuations of 1 part in 100,000, those ripples in the oldest light we can observe, the 67.4 they extracted from that map with an uncertainty of only half a kilometer per second per megaparsec, represents an extraordinary feat of precision and analysis. Both numbers are right in the sense that both have been checked and rechecked by independent teams using independent methods, and they keep coming back to the same places. And they can't both be right in the sense that both can't accurately describe the same universe under the same model. Something has to give. Either one of the measurements has an error that hasn't been found yet, or the model, LCDM, the framework we use to bridge from the infant universe to today, is missing an ingredient, and that missing ingredient, whatever it is, changed the expansion history of the universe between 380,000 years after the Big Bang and now. I want you to let that settle for a moment, because it's a genuinely strange thought. The universe was 13.8 billion years old last time anyone checked. Between 380,000 years old and 13.8 billion years old, something happened, or didn't happen, or something exists that we haven't accounted for, that changed the expansion rate enough that the prediction from the early universe and the measurement of the present universe are 9% apart. Something in those 13.8 billion years. Something in the history of the cosmos that the standard model is either not capturing or capturing incorrectly. And that thought, the quiet, precise 5 sigma thought, is what makes the Hubble tension not just a measurement problem, but potentially the most important open question in cosmology today. Not the only one. Science is full of open questions, and they exist at every scale from the quantum to the cosmic. But this one is unusual because it's so sharp. It's not a vague unease. It's not a conceptual puzzle about interpretation. It's 2 numbers that disagree at the level of 5 sigma, where 5 sigma is supposed to mean discovery. Except here, it's not discovering something, it's discovering a discrepancy, a fracture line in the standard model, a place where the recipe of the cosmos, as best we've been able to write it, might need a new ingredient. And the fact that it comes from 2 independent methods using completely different physics, pointing at the same disagreement from opposite directions, that's what gives it its weight. A single team getting a weird number is interesting. 2 teams using different tools with different histories of systematics, with different physics at their core, both confidently pointing at a mismatch. That's serious. You might be drifting a little now. Or, still listening very attentively, the lamp still on, the world quiet around you. Either is fine, there's nothing here you need to follow exactly. The shape of it is enough, the shape of 2 careful measurements built over decades, refined with the most powerful telescopes humans have ever made, landing on 2 different answers and refusing to move toward each other. That's the distance ladder and what it found. Parallax from the ground. Water mazes orbiting a black hole in a galaxy 23 million light-years away. Henrietta Swan Leavitt's careful eye on a photographic plate in 1912, discovering that the pulse of a star can reveal its distance. Type Ia supernovae burning through the darkness of billions of light-years, bright enough to see from here. Adam Riess and the Riess collaboration, climbing that chain rung by rung, arriving at 73. And then JWST launched, with the hope of finding the flaw, arriving instead with confirmation. 73 stands, 67.4 stands, and the gap between them, 5 sigma wide, 8 or 9% of the total, growing more solid with every refinement, is where the next chapter of cosmology might be written. We've come a long way tonight, you and I, from the infant universe and its frozen sound wave to the distance ladder and its chain of calibrated light. We've seen how two completely different methods using completely different physics look at the same cosmic expansion rate and see two different answers. We've seen how that disagreement deepens under scrutiny rather than dissolving, how JWST sealed off the most promising escape route, and how 5 Sigma transforms an interesting anomaly into something cosmologists can no longer simply wait out. But we haven't yet asked the question that's been waiting patiently behind all of this. If both measurements are right, or at least if neither is simply wrong, then what in the universe could explain the gap? What's in the recipe that we haven't added yet? That's where we're going next. And there are several candidates, genuinely fascinating, genuinely strange, each of which would, if confirmed, rewrite something fundamental about the cosmos we live in. Rest for a moment if you need to. Let the distance ladder settle. Let the sound of 73 sit beside 67.4 in your thoughts, like two quiet numbers that refuse to hold hands, waiting for someone to figure out why. We'll find out what the candidates are very soon. So let's talk about the witnesses. Because a courtroom with only 2 testimonies, even rigorous, carefully examined ones, can still leave a reasonable person uncertain. Maybe one witness is mistaken, maybe both are, in different ways. What makes a case airtight is when independent witnesses, people who don't know each other, who came from completely different directions, who use completely different methods, all point to the same defendant. Cosmology has been building that case, and the witnesses are starting to gather. The third one arrived from a completely different corner of the stellar population. Not Cepheids, not the brightness at which white dwarfs detonate. Something else entirely. Something you find at the very top of what are called the red giant branch stars. Here's what that means in plain terms. When a star like our Sun runs low on hydrogen fuel at its core, it expands, it becomes a red giant, that swollen, reddish, cooler stage that the Sun itself will enter in about 5 billion years. And as these stars expand and brighten, they trace a path along a well-understood sequence. They get brighter and brighter until they hit a very particular limit. At a certain luminosity, a helium flash occurs in the core, a sudden, brief ignition of helium fusion, and the star reorganizes itself. It steps off the ascending branch. That moment, that peak of brightness just before the helium flash, turns out to be almost exactly the same for every red giant of the right type. A fixed luminosity, a standard ceiling. It's called the tip of the red giant branch, and it gives you, if you can find these stars in other galaxies and measure how bright they appear to us, an estimate of how far away they are. Appear dim compared to what you know they should be. They're far away. Appear brighter, closer. Same principle as the Cepheids, but completely different stars, completely different physics underlying the calibration. Wendy Friedman's team, working through the Carnegie-Chicago Hubble program, the CCHP, spent years doing precisely this, finding the tip of the red giant branch in carefully chosen galaxies, measuring, cross-checking, arriving at a value for the Hubble constant that is, depending on the specific analysis, somewhere around 69 to 70 kilometers per second per megaparsec. 69 or 70, just hold that for a moment. Because that number sits, somewhat awkwardly, almost exactly in the middle. It's above what Planck and the cosmic microwave background predict, 67.4. And it's below what the SH0ES collaboration finds using Cepheids and Type Ia supernovae, roughly 73. Depending on which red giant calibration you use, which set of galaxies you anchor to, Wendy Friedman's measurements hover somewhere in that gap, neither fully endorsing the early universe camp nor the late universe camp. This is, honestly, one of the most important complications in the entire Hubble tension story. and it's one that a lot of popular coverage quietly steps around because it's awkward. It doesn't fit the clean narrative of two teams, two numbers, a clear battle line. The TRGB result says maybe the distance ladder is right, that the answer is higher than 67, but maybe it isn't quite as high as 73. Maybe the real answer is somewhere in the middle, or maybe the red giant calibration has its own subtle systematics, different anchor choices, different galaxy environments, different treatments of stellar population effects that shift its answer depending on how the analysis is done. Wendy Friedman and her collaborators have been very careful, and the ongoing debate between the TRGB result and the Riess result is a genuine, active, collegial disagreement happening right now in the scientific literature. What it tells us, at minimum, is that the late universe camp is not a monolith. It's not simply one side saying 73 and the other side saying 67. There's a third voice in the middle saying, I've used a completely independent standard candle and I'm getting something that doesn't quite agree with either of you. And that complication is strangely reassuring, not because it makes things cleaner, but because it means scientists are being honest. A field that quietly suppressed awkward intermediate results would look tidier. A field that publishes them and argues about them openly is a field doing what it's supposed to do. So the TRGB result is witness number 3. It doesn't fully corroborate the Riess value, but it also doesn't fully support the Planck prediction. It sits in the tension, not outside it. Now, fourth witness, and this one is stranger than all the others. In September of 2017, two neutron stars collided. They had been spiraling toward each other for a very long time. These incredibly dense, city-sized remnants of supernova explosions, each packing roughly the mass of the Sun into an object perhaps 10 miles across. As they circled closer and closer over millions of years, they radiated energy in the form of gravitational waves, ripples in the very fabric of space-time, predicted by Einstein a century earlier, first directly detected by LIGO and Virgo in 2015. And in the final moments before they merged, those gravitational waves washed across the Earth and were detected. A chirp in the instruments, a record of the final spiral. The event was called GW170817 for gravitational wave 2017, August 17th. And it was remarkable for more than one reason. Here is the key thing about a gravitational wave signal from a merging pair of compact objects. The waveform itself, the precise shape of the chirp, the way the frequency and amplitude evolve as the objects spiral inward, encodes the absolute distance to the source, not a distance relative to something else, not distance inferred from brightness and assumed luminosity. The gravitational wave signal carries its own distance scale, baked in by the physics of general relativity. This is what astronomers call a standard siren. Instead of a standard candle, something whose brightness tells you how far away it is, a standard siren is something whose sound, so to speak, tells you how far away it is. GW170817 also had something else. It was accompanied by a burst of light, a kilonova, a brief, intense glow produced by the material flung outward in the collision. And that glow had a precise position on the sky in a galaxy called NGC 4993, about 130 million light-years away. So you knew the host galaxy, you knew its recession velocity from independent spectroscopic measurements, and you knew the distance to the merger from the gravitational wave signal alone, with no ladder needed. No Cepheids, no supernovae, no red giants. The value they derived for the Hubble constant from GW170817, around 70 kilometers per second per megaparsec, with fairly large uncertainties because it was only one event, and because the inclination angle of the binary system, which affects how the signal looks, was not perfectly constrained. But it was there. An entirely independent measurement, using physics that has no connection to stellar brightness, no dependence on the period luminosity law, no chain of calibrations. Just the shape of a ripple in space-time and what it tells us about how far away it was. Right now, the standard sirens measurement is imprecise. The error bars on 70 are wide enough that they're consistent with both 67 and 73. To really adjudicate the Hubble tension, you'd need many more events, dozens ideally, with known host galaxies and well-constrained inclination angles. That's coming. Every new LIGO and Virgo observing run adds more. Future detectors, including planned space-based instruments, will add vastly more still. The standard sirens measurement is not yet sharp enough to be decisive, but here is what it is: a completely independent third category of evidence built on completely different physics, pointing to a value somewhere in the middle. And as its precision improves over the coming years and decades, it will become a more and more powerful voice, either supporting one camp or adding yet another independent line of data to an already complicated picture. Fifth witness: light bending around galaxies and what it reveals about time. If a very distant, very bright object, a quasar, happens to sit behind a massive galaxy or cluster of galaxies, from our perspective, something interesting happens. The mass of the foreground object bends the path of the light coming toward us. Instead of traveling in a straight line, the light from the quasar follows the curved geometry of space, and it often splits into multiple images. You see the same quasar in 2 or 3 or 4 places in the sky simultaneously, each image formed by a different path the light took around the lensing mass. Now, those different paths have different lengths, and if the quasar is variable, if it flickers and pulses as quasars do, you see the same flicker arrive at Earth from each image at slightly different times. The image whose light took a shorter path around the lens sees the flicker first. The image whose light took a longer path sees it later. That time delay, measured in days to weeks, encodes, if you know the geometry of the lens well enough, the Hubble constant. Because the length of those paths depends on the scale of the universe, which depends on how fast it's been expanding. Several collaborations have spent years doing precisely this. The H0 program, standing for H0 lenses in Cosmograil's wellspring, which is a name that reveals a certain enthusiasm for acronyms. And later, the TD Cosmo collaboration gathered systems of lensed quasars with measured time delays, and their early results, taken at face value, pointed toward a high value, close to 73, similar to what SH0ES finds from the distance ladder. Later reanalyses, which relaxed some of the assumptions about the mass distribution in the lensing galaxies, widened the error bars considerably. It turns out that how you model the lens matters enormously. The distribution of matter in a galaxy or cluster is complex, and different assumptions about that complexity shift the inferred Hubble constant. So the strong gravitational lensing route has its own internal debates, its own systematic uncertainties. But again, the method is completely independent. It uses the geometry of curved space-time and the variability of a distant quasar. It has no overlap with Cepheids, red giants, supernovae, or the cosmic microwave background, and in its most straightforward analyses it tends to lean toward the higher values, 6 witnesses now, and a 7th from a completely different direction. The Dark Energy Spectroscopic Instrument, DESI, has been mapping the 3-dimensional distribution of galaxies across the universe from its perch at the Kitt Peak National Observatory in Arizona. When you look at where galaxies cluster in space, you can see, imprinted in that distribution, the same baryon acoustic oscillations we talked about earlier, the same sound wave signature, the same 150 megaparsec ruler, but written not in the cosmic microwave background, but in the pattern of galaxies themselves across a huge swathe of cosmic time and space. DESI has been running since 2021, and its 2024 and early 2025 data releases have offered something genuinely surprising, though it's connected to the Hubble tension sideways rather than directly. The DESI measurements of baryon acoustic oscillations are consistent overall with the broad picture of the standard LCDM model. But when they're combined with other data sets and analyzed carefully, they hint, and it's still a hint, not a firm detection, that dark energy may not be constant. That the 68% of the universe's energy content we call dark energy, which we've been treating as a fixed, unchanging cosmological constant since we first detected the accelerating expansion in 1998, might be something that varies over time. This is a separate story from the Hubble tension, but it's not unrelated, because one of the proposed solutions to the Hubble tension involves dark energy behaving differently in the early universe than it does now. If dark energy isn't constant, if it evolves, then DESI's independent hints of evolution are, at minimum, consistent with a universe that is more complicated than our standard model assumes. It doesn't solve the tension. DESI's results don't directly tell us why 67 and 73 disagree, but they do suggest that LCDM, the standard model that predicts 67.4 and has been performing so well for 2 decades, may be showing cracks in more than one place. That 2 independent kinds of data, the Hubble tension and DESI's dark energy hints, are both pointing toward the same general idea, that the recipe of the cosmos may need a new ingredient. And all of this brings us to the menu. If the tension is real, if it's not a measurement error that someone will eventually find and correct, then what could explain it? What would have to be true about the universe to make 67.4 and 73 both correct simultaneously? There are several serious candidates. None is confirmed. Each carries its own complications, its own strains on other data, its own beauty, and its own awkwardness. Let's walk through them slowly. The leading new physics candidate is called early dark energy. You'll remember that the 67.4 comes from taking the cosmic microwave background with its precise snapshot of the infant universe and running the standard LCDM model forward 13.8 billion years to predict what the expansion rate should be today. And you'll remember that the key physical ruler in that process is the sound horizon. The distant sound waves could travel through the hot, dense plasma before recombination froze everything at around 380,000 years after the Big Bang. We measured that sound horizon to be about 150 megaparsecs, or roughly 480 million light years. Here is the crucial thing. The predicted Hubble constant is sensitive to the size of that sound horizon. If the sound horizon were smaller, if those frozen ripples were compressed closer together, then the prediction for how fast the universe should be expanding today would be higher. It would move upward towards 73. Early dark energy is the idea that there was a brief burst of extra energy density in the early universe, a few 100,000 years before recombination, or perhaps right around that time, that temporarily accelerated the expansion slightly. This extra push would have compressed things. The sound horizon would have been slightly smaller than our standard model assumes. The frozen ruler would be shorter. And if you then run LCDM forward with that smaller ruler, you'd predict a higher Hubble constant today. High enough, potentially, to reconcile the two measurements. It's a genuinely elegant idea. It doesn't require changing the late universe physics. The supernovae, the Cepheids, the distance ladder are all fine. It requires adding something small and brief to the very early universe, something that went away quickly and left only its fingerprint in the compressed sound horizon. But there's a catch. There are always catches. Early dark energy has to switch on and then switch off at just the right time. Too early, and it leaves other imprints in the microwave background that we don't see. Too late, and it doesn't affect the sound horizon enough. The fine-tuning required, The precision with which this hypothetical early dark energy would have had to appear and disappear is uncomfortable for many cosmologists. Fine-tuning arguments in physics are warnings. When a theory requires its parameters to take very specific, very delicate values, nature doesn't usually oblige us that precisely without a reason. And early dark energy also tends to make other cosmological tensions worse. There's a separate, gentler tension related to the clustering of matter in the large-scale structure of the universe, encoded in a quantity called S8, and early dark energy tends to strain it. Solving one problem by introducing another isn't a satisfying resolution. So early dark energy remains the front-runner among new physics candidates, but it's the front-runner in a race where no candidate has yet crossed the finish line. The second possibility is related, but broader. What if dark energy itself isn't constant? The lambda in LCDM stands for the cosmological constant, the fixed, unchanging energy density of empty space that drives the accelerating expansion. We've assumed it's constant because that's the simplest model and it's fit the data well. But there's no fundamental reason it has to be constant. It could be a field. Physicists often call a dynamical dark energy field quintessence, that evolves slowly over cosmic time. If dark energy was slightly different in strength in the early universe than it is now, that could change the geometry of the expansion history in ways that might, depending on the specifics, relieve some of the tension. The DESI hints of evolving dark energy are relevant here because they're independent evidence from the galaxy distribution, not the CMB, that lambda may not be as lambda-like as we've assumed. Whether evolving dark energy is the answer to the Hubble tension specifically is uncertain. The observational constraints are complex, but it's a live and serious possibility, and it's the kind of modification to the standard model that would, if confirmed, be genuinely fundamental. Not a small adjustment. A change to one of the most basic ingredients in the cosmic recipe. Third possibility. What if there are more kinds of particles in the early universe than we know about? In the standard model of particle physics, there are three kinds of neutrinos. Ghostly particles with almost no mass that barely interact with anything, produced in enormous numbers in the early universe and still streaming through you right now, trillions of them every second, like a quiet ghost river through your body and the room around you. The number of neutrino types, along with any other light particles present in the early universe, is encoded in a quantity cosmologists call Nef, the effective number of relativistic species. Currently, Nef is measured to be close to 3. But what if there's a fourth? A dark radiation, some light, fast-moving particle that doesn't interact through the electromagnetic force, invisible to our detectors, but still contributing energy density to the early universe. An extra bit of Nef would also affect the sound horizon. It would change the timing of recombination and the dynamics of the plasma in ways that shift the predicted Hubble constant upward. Like early dark energy, this would compress the effective ruler. And unlike early dark energy, it wouldn't need to switch off. It would just be there, another permanent component of the cosmic inventory. The problem is that Nef is already quite tightly constrained by the CMB data itself. Adding a full new neutrino species, Nef increasing by 1, is strongly disfavored, but a partial extra contribution, something smaller, remains viable. It's been explored, it's constrained, and it illustrates a general principle. Any modification to the early universe that changes the sound horizon is, at least in principle, a candidate for lifting the predicted Hubble constant towards 73. And then there's the fourth possibility, the one that the careful scientist keeps returning to before all others. What if there's a systematic error we simply haven't found yet? This is the boring answer, the answer that doesn't require new physics. The answer that says the distance ladder has a flaw, or the CMB analysis has an assumption that's not quite right, or something in the chain of calibrations is subtly off in a way that hasn't yet been caught. Cosmologists have been stress testing this possibility for years. They have checked the Cepheids, they have checked the supernova samples, they have rechecked the Cepheid crowding and blending, suspecting that when Cepheids are imaged in dense stellar fields with the older, less sharp optics of Hubble, some fraction of their light might be contaminated by neighboring stars, biasing their measured brightness and therefore their inferred distance. James Webb was supposed to be the instrument that settled that. And it checked. And it found that the crowding problem was real at some level, but not large enough, not by far, to close the gap. The JWST-based analyses by the S80ES team and others consistently found that yes, Webb's sharper infrared imaging gives better Cepheid measurements. And yes, those measurements agree with what Hubble found within the error bars. The systematic escape route was tested thoroughly. The door was locked. Could there still be something undiscovered? Yes, in principle. Science can't prove a negative. There could be a systematic error lurking somewhere that every current test has missed. But the burden of proof grows heavier each year as more and more independent checks come back without finding it. The systematic error hypothesis is still alive. It's just lost a lot of its hiding places. This is what makes the Hubble tension in 2025 a genuinely serious open problem rather than a housekeeping matter. It's not just one team with one method saying something unusual. It's a constellation of independent lines of evidence built on different physics, maintained by different collaborations, arriving at values that disagree, and that disagreement persisting and sharpening over years of refinement. And at this point, a thoughtful person lying quietly in the dark might think, we've seen scientific tensions before, haven't we? Haven't cosmologists been wrong about the Hubble constant before? Yes. Emphatically, yes. And this is the part of the story that's worth sitting with, because the history is a genuine cautionary note. When Edwin Hubble published his measurements of cosmic expansion in 1929, he derived a value for what we now call the Hubble constant of around 500 kilometers per second per megaparsec, 500, against our current values clustered around 67 to 73. He was off by a factor of roughly 7. This wasn't sloppiness. Hubble was working with the best instrumentation of his era, and his analysis was careful by the standards of the time, but he was using a flawed Cepheid calibration. He was working with relatively nearby galaxies. He was operating before the distinction between two different kinds of Cepheid variables was understood: population 1 and population 2 Cepheids, which have different period luminosity relations. When Walter Baade revised the Cepheid calibration in the 1950s, the implied Hubble constant dropped dramatically. But then for the next 4 decades, the field was split. Alan Sandage, one of the most meticulous observers in the history of astronomy, spent his career arguing for a value of around 50 kilometers per second per megaparsec. Gérard de Vaucouleurs argued with equal conviction for a value around 100. The two camps went back and forth, publishing, arguing, recalibrating, disputing. It became known within cosmology as the Hubble War, 2 numbers, a factor of 2 apart. Each camp convinced the other was systematically wrong, and each camp was right that the other had some systematic errors, and also right that they themselves had some. The field eventually converged through the work of multiple teams in the 1990s and early 2000s, on a value in the range of 65 to 75, eventually settling into the modern consensus around 70, which is where the Hubble Space Telescope Key project arrived in 2001. So yes, the history teaches humility. We've had a Hubble crisis before, we cried tension before and resolved it with better measurements and corrected calibrations. The possibility that the current 5 sigma gap will similarly dissolve, that some careful reanalysis will locate the error and bring the two values together, is not zero, it's not negligible. Several serious cosmologists maintain that view today, but here is why this time is different, or at least why most cosmologists believe this time is different. The first Hubble war was fought entirely on the distance ladder. Different groups were using different rungs, different calibrations, different samples of galaxies, and arriving at different values because they were making different choices about the same basic method. The systematic errors were internal to the ladder. The debate could be resolved by building a better ladder with more careful calibrations and better understanding of the stellar physics involved. The current tension is between two entirely separate categories of method. Not two groups using the same technique differently, but two fundamentally different approaches. One measuring the early universe and running a model forward, one measuring the late universe directly, that disagree, and the tension is corroborated by independent lines within each camp. It's not just Planck versus Cepheid, it's Planck plus the entire early universe picture built on baryon acoustic oscillations versus Cepheids plus TRGB plus standard sirens plus lensed quasars, all clustering on higher values. And it's at 5 sigma. The Hubble war was never at 5 sigma. Even at its most intractable, it was a disagreement measured in a small number of standard deviations, with error bars that often overlapped, with enough ambiguity in both calibrations that a reasonable person could imagine where the error was hiding. At 5 sigma, with a probability of a statistical fluke around 1 in 3.5 million, the burden shifts. You need a real explanation. Either there's a systematic error somewhere that has survived every test applied so far, or the universe is telling us something about itself that our model doesn't yet contain. That's the honest picture. Not scientists are baffled, and nobody knows anything. Not the whole standard model is broken and everything we thought we knew is wrong. Something more precise and more interesting than either of those. Two extremely careful measurements built on completely different foundations, giving answers that differ by about 8 or 9% at a level of statistical significance that in any other context would be called a discovery, with a growing collection of independent checks that tend to lean toward the higher value but haven't yet made it unanimous. With several fascinating candidate explanations: early dark energy, evolving dark energy, dark radiation, undiscovered systematic error, none yet confirmed. With a brand new generation of instruments, JWST for the ladder, DESI for large-scale structure, gravitational wave detectors for standard sirens, improved CMB experiments, adding data and sharpening constraints with each new observing run. It's the most exciting open question in observational cosmology right now, and it has been building slowly, carefully, through years of meticulous work by hundreds of researchers to the place where it stands tonight, a contradiction, 5 sigma wide, between what the early universe predicts and what the late universe shows, a gap that widens as the measurements get better, a possible missing ingredient in the recipe of everything. And you are lying here, in the dark, made of that universe. Think about that for a moment. Really think about it. The matter in your body, the atoms that are slowly breathing in and out as you rest, were forged in the hearts of stars. The hydrogen, the simplest element, was made in the first few minutes after the Big Bang, in the heat and density of the early cosmos. The heavier elements, the carbon in your cells, the oxygen in your lungs, the iron in your blood, were cooked in stellar interiors and scattered by supernova explosions across billions of years of cosmic history. You are, in a very literal sense, the universe's matter remembering itself. And the expansion that the Hubble constant describes, that relentless stretching of space, that recession of galaxies from each other at speeds proportional to their distance, that expansion is happening right now while you rest. The Virgo cluster, tens of millions of light years away, is receding from us. The great galaxy clusters at the edge of the observable universe are retreating at speeds approaching the speed of light, not because they're moving through space, but because space itself is carrying them away. The observable universe is a bubble 93 billion light-years across and growing, and we don't know quite precisely how fast. We know it's somewhere between 67 and 73. We know it's close to 70. We know that the answer matters, not just as an intellectual puzzle, but because the Hubble constant tells you the age of the universe, the size of the observable universe, the ultimate fate of everything. Whether the universe will expand forever, or whether dark energy will eventually tear apart galaxies, then stars, then atoms themselves in a scenario called the Big Rip. These things depend on the precise nature of whatever is driving the expansion. A tiny change in the recipe of the cosmos, an extra ingredient we haven't identified yet, could resolve 67 and 73 into a single answer. And that resolution, if it comes, will be one of the great scientific moments of this century. It'll probably come with a quiet announcement in a scientific journal, a paper submitted on a Tuesday, reviewed over weeks, published with a restrained abstract and careful error bars. The discovery of a missing cosmic ingredient rarely arrives with fanfare. But for the people who have spent careers measuring this single number, working in cold observatories at altitude, debugging pipelines and testing calibrations, and arguing over systematic errors in conference rooms, for them it will be enormous. Adam Riess, who shared the Nobel Prize in 2011 for the discovery of accelerating expansion, has spent much of the years since then sharpening the measurement of 73. He knows better than almost anyone how hard it is to get this right. The SH team that he leads has been through every objection, every proposed systematic, every raised eyebrow, and they keep arriving back at the same answer. Wendy Friedman and her collaborators at the Carnegie-Chicago Hubble program have spent equal care arriving at their intermediate value and defending it. Two meticulous, rigorous groups, both correct in their internal logic, arriving at answers that don't quite agree even with each other, let alone with Planck. And somewhere at CERN, or in the offices of the DESI collaboration in Tucson, or in the data pipelines of LIGO and Virgo, the next piece of evidence is being processed right now. Galaxies being catalogued, gravitational wave signals being analyzed, dark energy constraints being tightened, the universe is being measured, carefully, painstakingly, one standard candle and one standard siren and one lensed quasar at a time. We don't have the answer tonight. I should be honest about that. Nobody does. The Hubble tension is a genuinely open problem in the most rigorous sense, not a mystery invented for drama, not a minor footnote, not a question whose answer is already known, but just waiting for a press release. It is a 5 sigma discrepancy between two well-established measurements, and the resolution, when it comes, will require either the discovery of a systematic error that has survived extraordinary scrutiny, or the addition of a new ingredient to our model of the cosmos. Both are remarkable outcomes. Either one will teach us something new. And sitting with that openness, that genuine, honest, evidence-backed uncertainty, is a particular kind of pleasure if you let it be. Because the universe doesn't owe us comprehension on a human timetable. It has been expanding for 13.8 billion years without consulting anyone's publication schedule. The Cepheids were pulsing in their distant galaxies long before Henrietta Swan Leavitt in 1908 noticed the pattern in her photographic plates at the Harvard Observatory, long before anyone imagined that their rhythm could be used to measure the scale of everything. The cosmic microwave background was washing over the Earth long before Arno Penzias and Robert Wilson found it accidentally in 1965, mistaking it at first for interference from pigeon droppings in their antenna. The gravitational waves from merging neutron stars were rippling through space-time for 130 million years, from a galaxy called NGC 4993, where two stellar ghosts spiraled toward each other before they arrived on Earth in August of 2017 and caused the most sensitive instruments humanity has ever built to shudder by an amount smaller than a proton's width. We discover these things on our own time, not the cosmos's. And there is something humbling and comforting about that, if you're in the right mood to receive it. You might drift off tonight carrying a small, unresolved question, 67 or 73? What's in between? What is the universe doing that our recipe doesn't account for? That's fine, that's actually quite good, I think. The most interesting questions are the ones you can carry into sleep and find waiting for you in the morning, unchanged, patient, deep. Back at the beginning of tonight, before we had talked about any of this, I described a gap. Two numbers that refuse to meet. A disagreement precise enough now to carry a name and a significance level and a growing literature of proposed solutions. What I hope you have now is a sense of what that gap is made of, not just the numbers, 67.4 and 73, but the machinery behind them. A satellite mapping the afterglow of the Big Bang at one part in 100,000, running a model forward through 13.8 billion years. A chain of calibrated light stretching from the nearest stars to the farthest reaches of the Hubble flow, rung by rung, Cepheid to supernova. A new telescope that was supposed to collapse the chain and instead confirmed it. Red giant stars tipping at a fixed luminosity in galaxies Wendy Friedman's team spent years measuring. A chirp in a gravitational wave detector. A neutron-star collision 130 million years in the making, arriving at LIGO in 2017 as a distance measurement with no ladder needed. Quasars flickering behind lensing galaxies, their delays encoding the Hubble constant in the geometry of curved space-time. All of these witnesses, all of these independent methods, all pointing to a tension that has not dissolved, and you are part of the universe those measurements describe, the same atoms, the same physics, the same expansion happening right now, carrying every galaxy away from every other galaxy, including the ones whose distances have been measured so carefully that two extraordinary scientific teams can agree on the measurement and disagree on the meaning. It's an enormous thing to hold. It's also, I think, a good thing to drift to sleep on. The universe is strange and it is knowable, and we don't know all of it yet, and that's all right. We're getting closer, slowly, carefully, one careful measurement at a time. If you've enjoyed coming on this slow journey through the cosmos tonight, a gentle like and subscribe really helps this sleepy little channel keep going. Small creators like me truly rely on your support to keep making nights like this one. And if you feel moved to leave a word before you drift off, I'd love to know, where in the world are you listening from tonight? And what time is it in your corner of the universe? Until then, sleep well. The expansion will still be happening when you wake up. Good night, kiddo. Grandpa'll leave the porch light on.